Our Placerita Canyon woodpecker endured a whopping 1,500 G while pecking. But we don't know how much more woodpeckers can endure before injury. Let's use what we know about human brain injury to figure out the limits of the woodpecker's tolerance. It turns out it's all a matter of scale. A force is a mass times an acceleration, or in this case, a deceleration. But it turns out it's not quite that simple. What really matters is the force divided by the area that the force is applied over. Imagine you have a rope, and say you apply a tensile force to it, and you find that the rope breaks when you apply 1,000 pounds of force. So now imagine if you had two identical ropes, the force to break those would be 2,000 pounds, just twice as much because you've got twice the area. And so what really matters isn't just the force, it's the force divided by the area. So if we think of the brain and the skull, as the woodpecker's head hits the tree, both of these things are decelerating as the head decelerates. And we can say that the impact force for the woodpecker is the mass of the woodpecker brain times the deceleration that it undergoes when it hits the tree. And we're going to divide that by the area of contact between the brain and the skull. The force per unit area to cause damage is similar in different species. So let's relate the impact force per unit area for the woodpecker to that of the human and solve for deceleration, or dW. We can simplify this somewhat by saying that both the mass and the area depend on the size of the brain. So the mass depends on how big the brain is, the volume, and that goes as the radius cubed, and the area goes as the radius squared. So in both cases, canceling out, the radius times the deceleration that the woodpecker brain can tolerate before injury is equal to the radius times the deceleration that the human brain can tolerate before injury. The deceleration that the brain can withstand without injury depends on its size. This is an example of a scaling law. The size matters. The smaller the brain, the larger the deceleration that it can withstand. But we have to look at the area in a bit more detail. And here we have two skulls. We've got one for a human here and one for an acorn woodpecker over here. And we want to look at the orientation of the brain, because the orientation of the brain affects the contact area that comes into our scaling law. The brain's roughly a hemisphere, and in the human brain, the hemisphere is oriented something like this. And so when the impact occurs in the human brain hits the front and hits the back of the skull, and the area of contact is roughly this half area here. If we look at the acorn woodpecker skull, you can see that the back of the skull here that is protecting the brain is actually oriented more in this direction here, so that as the woodpecker pecks and the brain sort of moves forward and backwards in the skull, then it's the entire area of this hemisphere that is the area of contact. So relative to the human brain, there's an increased area by a factor of 2 for the woodpecker brain. So we have to incorporate that into our scaling law. The factor of 2 for the woodpecker brain is somewhat approximate. At the back of the brain, it's a reasonably good approximation. At the front, things are more complicated. In the tennis ball analogy, the vertical slice at the front has a plain circular cross-section, which does not increase the area by a factor of 2. But the surface of the brain is curved so that the area is larger than in our analogy. For simplicity, we use a factor of 2 here. And we find that there's this factor of 2 times the radius of the human brain over the radius of the woodpecker brain times the deceleration in the human. So the next thing we need to know is the ratio of the size of the human and the woodpecker brain. And much to my amazement, I found a paper called Brain Size in Birds. This paper, Brain Size in Birds, had table after table for many different species of birds, and they had measured the bird brain mass. And from the mass, you can estimate the size. The human brain is about 8 times the size of the woodpecker brain. The woodpecker brain was about 2.5 grams, and the human brain is about 1,400 grams. So our equation says that the woodpecker brain can tolerate a deceleration 16 times that of the human brain. So this is kind of interesting. We said that the human brain could tolerate 100 G. So our equation so far says that the woodpecker could tolerate something like 1,600 G. And if you recall the measurements that the neurologists made, the woodpecker was pecking and sometimes reached decelerations of 1,500 G. So the other factor that comes into play is the duration of the impact. People have studied human brain injury quite extensively, and they found that if the duration of the impact is shorter, the brain can withstand a larger deceleration. So this graph shows some information that's been obtained from human brain injury, and on the graph we've superimposed the region over which a typical human head impact occurs. So typically for human head impacts, things like football player injuries or car crashes, the impact occurs over something like 3 to 15 milliseconds. And we can take this curve here for the humans and we can simply scale it up by our factor of 16, and then we remember that the typical duration of the acorn woodpecker head impact was between half a millisecond and 1 millisecond. You can see that the tolerable deceleration is something like 4600 G to 6000 G. And also on this graph, we've superimposed the measured decelerations during pecking, and you can see they're substantially below that amount that we're estimating. So this all kind of makes sense that the tolerable acceleration is really much higher than what you would measure during pecking. So if we summarize what we found here, we can say that there's really 3 factors that have allowed the woodpeckers to tolerate these high decelerations. One is their small brain size, that was a factor of 8. One is the orientation of the brain, that gave another factor of 2. And one is the duration of the impact, and that gives a factor of 4. So that altogether there's a factor of 64. The woodpecker brain should be able to withstand decelerations about 64 times that a human brain can tolerate without injury.